Hey guys, welcome back to our Aerospace Engineering lecture series. I am Dr. K. Nehru and today's topic aircraft wing as a vibrating system, which means that we are understanding the aerospace phenomena, vibration mode and flutter instability in aircraft wing structures. Aircraft wings are not preferred rigid structure. They bend, twist and vibrate under aerodynamic load. Understanding this vibration is essential to ensure safety, performance and structural integrity. In this session, we will study wing structural component, vibrating modes, aeroelastic flutter, testing methods and modern engineering approach used to control this phenomena. Let's begin our journey into the fascinating world of aeroelasticity. To understand wing vibration, we must first understanding wing construction. A spar are the primary load carrying member of the wing resisting bending force during flight. The rib maintains the aerofoil shape and distribute aerodynamic loads. The skin forms the aerodynamic surface and contribute to the structural stiffness. Together these elements create a complex flexible system. Every wing possesses natural frequency which represents its performed vibrating patterns. Associated with each natural frequency is a mode shape that describes how the wing deforms. Depending damping mechanism includes material damping and aerodynamic damping helps dissipate energy and reduce excessive oscillation in the wing. So let us see this wing diagram and different spars are located in the wing in the Concorde aircraft which observe the basic vibration in the system like natural frequency, different modes and damping which dissipates the energy in the wing. Next, coming to the vibration modes, aircraft wing exhibits several important vibration modes. The first is symmetric bending, where both wings moves up and downward together. This is often the fundamental modes of vibration. The second mode is asymmetric bending of the wing, where one wing moves upward and while the other one moves downward, creating the complex wing structural interaction. The third mode is symmetrical torsion involving equal twisting of both wings. Finally, the antisymmetric torsion occurs when the wing twist is opposite direction. These modes determine the natural frequency of the aircraft and significantly influencing in the aeroelastic stability as well as the instability. Understanding these deformation patterns helps engineers to design safer and more efficient aircraft wing structure. One of the most critical challenges in the aerospace engineering is flutter. Before flutter occurs, another phenomenon called divergence may appear. Divergence is a statics instability in which aerodynamic forces overcomes structural stiffness, causing uncontrollable deformation. Flutter, however, is a dynamic instability. It results from the coupling between bending and torsional vibration. As a critical airspeed called the flutter speed, energy from the airflow continuously feed into the structure, causing vibration amplitude to the growth rapidly. If not controlled, flutter can lead to catastrophic structural failure. This is why every aircraft undergoes extensive flutter analysis and testing before the aviation certification. Coming to the design thinking approach, modern aerospace engineering increasingly adopt design thinking principles. The first type is empathizing the problems and understanding how vibration is created, condition pilot requirements and possibility of failure mechanism in various locations of the aircraft, especially engines, wings and the landing gear. The next come to the define and identifying the natural frequency, rather flutter limitations and the damping needs. We are coming to the ideate and giving the solution to the usage of composite material, turn mass, dampers and active control systems. During the prototype, the engineers develop simulation models and physical testing articles where the final test will be evaluated during the using of wind tunnels and the flight testing machines. These structural approaches encourage creative while maintaining engineering rigorous design. Coming to the vibration analysis method, several experimental techniques are used to study different vibration observations. The first is a modal analysis, which determines natural frequency and the mode shapes. Impact test using a hammer strike to excite the natural and the structural measurement when due to this response. Shaker tester provides control harmonic inputs over a range of frequency to identify resonance condition. Strain gauge measures local deformation and the stress concentration during vibration. The modern aerospace laboratory combined these methods with a digital simulation to create high accurate predictive models. These tools enable engineering to detect potential aeroelastic issue before actual the flight is operated. Now coming to the aircraft wing vibration mind map to gather all the concepts discussed so far. At the center lies the aircraft wing as on the vibrating system. The structural branch includes spar, ribs, skin and stiffness. The vibration branch highlighted the bending and the torsional modes during the oscillation. The flutter branches focus on aeroelastic instability, energy exchange, divergence and flutter speed limitation. Design thinking branch illustrate the cycle of empathy, define, ideate, prototyping and testing. Finally, the analysis method such as model testing, impact experiments, accelerometers and strain gauge provides practical tools for engineers. This integrated framework helps us to understand and control wing vibration effectively. Finally, let us summarize today's session. Aircraft wings are flexible structure composed of spar, ribs and skin that determine their vibration characteristics. Different bendings and torsional modes define the natural frequency of the system. Flutter response is a dangerous elastic instability that may be carefully predicted and prevented. Experimental methods such as model analysis, shaker, testing and the strain measurements plays a crucial role in the validating theoretical model. By integrating design thinking of principle, engineer develops innovative solution for vibration control and the structural optimization. Further development includes advanced composite material, active flutter support technology, and real-time structural health monitoring systems. Understanding aircraft wing vibration is fundamental to design a safer, lighter, and more efficient in aerospace vehicle. Thank you for watching. If you are enjoying this lecture, please like, share, and subscribe for more aerospace engineering content. See you in the next section. Thank you.